Hello. In this video, I will show you how to use Bosch Rexroth XM22 control as controlled area network receiver. Our control is equipped with CAN bus extension module XFE01.1-FB-20. You can find additional detailed information about this module in manual IndraControl XFE01.1 extension modules, part number R911345570. As a source of our CAN bus messages, we'll use Never Die Battery Management System by Lithionics Battery. To program our control, we'll use latest version of IndraWorks Engineering software. So first, we'll create new project and name it XM22 CAN bus. It shows up in Project Explorer. Next, we can select our control type in the library, and then we can drag and drop it into our new project. Next, new window shows up, and here we can configure our control. In the first step, we can change the name of the control, but we'll keep default name. In the second step, we can configure a communication to our control. A default IP address for new XM22 control is 192.168.1.1, so we can execute connection test and verify proper communication. In step 3, we keep all default settings. In step 4, we only need to select PLC and OPC UA function packages, and all other packages can be deactivated. In step 5, we can deactivate circuits interface, and then we must select our attached extension modules. But as you can see, we are using a module CAN XFE01, and it's not on our list. So next, we'll add this module to our project. CAN XFE module can run in many different operating modes, and for any one of them, we can provide you with special, dedicated description files. And in our case, we need latest version of file EM CAN XM device description. Back in our program, to add module, we go to Tools, then Device Database, and then Add Devices. Next, we can select our description file from the list and see it added to our database. Next, we can go back to our control configuration again and finish step 5. Now our CAN module shows up on the selection list and can be added to our project. Then, after we click Finish, it will take a couple seconds and our configured control shows up in Project Explorer. When we click on it, new editor shows up and we can work on our PLC logic. Of course, we can write everything ourselves, but much more efficient and much faster is to use a library. So we'll use proven and tested Codesys CAN bus example library, available for download at Codesys Store International. After download, we receive a package CAN bus API, and after we open it, in subdirectory component and library, we can find our file CAN bus API.library. Next, we'll import this library into our project. So first, we'll open Library Manager window. Here you can see all default libraries automatically included in our project and ready to be used. Then we go to Library Repository and click on Install. Selection window shows up, and here we can pick our library file. Back in Library Repository, we can see our library installed under Application Utilities. In the last step, we'll add this library to our project. So we click on Add Library, then select our library from Library Repository. And right away, our library shows up in our list, ready to use. When we click on this new library, we can see its internal elements. We can see enumerations available for us, function blocks for both graphical and object-oriented programming. In our case, we use object-oriented function block CAN bus 29-bit. And here we can see all methods available for this function block. Under Interfaces, we can see an interface iMessage processor with supporting method. And under Structs, we can see all structures used by this library. Now we can start to work on our PLC logic. And first, we must create a function block to process messages. So we right-click on Application, then Add, and then POU. We name it Message Processor _ST for structured text. We make sure it is set as function block, and then we implement into it interface iMessage processor from our CAN library. Our new function block shows up in Project Explorer together with the method ProcessMessage. When we open it, we can see implementation, and when we open a method, we can see that variable message for incoming messages is automatically declared for us. Now, let's look at standard CAN extended data frame. And we can see that first part of every message is identification, followed by control and data fields. So first part of our logic in message processor will be extraction of identification from incoming messages. To do that, we create new variable receive CAN ID and write into it part of the message extension UD CAN ID. System automatically opens for us auto-declare window for new variable. And here we set a type to UDINT. Also, please note that this variable will be used globally by other programs. And there is a global variable list, user var global, already created in this project. So in auto-declare scope selection, we pick var global, and as object, our user variable global list. And right away, we can see that our variable was added to global list. Back in our method, please note that there is a pragma warning, add method implementation, and we can delete it. Next, we'll add new program to send and receive CAN bus messages. So we add new POU, name it PR CAN underscore send receive, make it type program, and leave structured text as implementation language. Our new program shows up in Project Explorer and we can open it. But before writing new logic, let's look into our library again. Here we can look into the description of function block we want to use. This function block named CAN bus 29-bit can handle messages with 29-bit CAN IDs. We can see here that this function block requires configuration and has a special input and data structure for it. When we click on this type, we can see that this structure has three elements. Baud rate, typically 250 kilobits per second. Network ID starts with 0. And length of outgoing messages, typically set to 10. So in our logic, first I'll put some comments for our declaration. Then declare new function block driver CAN 29-bit, and as a type, use our function block CAN bus 29-bit from library CAN. Next, we'll add the configuration variable for this function block. So we create new variable st CAN bus config, type driver config from library CAN. We know that this variable is a structure and we need to start it with initial values. We can set those values here in declaration, but if we are not sure about syntax, we can switch our declaration editor to tabular view and click here on Initialization field. New initialization value window opens up, showing all elements of our structure. So here we can put value 250 for baud rate, 0 for network ID, and 10 for message length. Our initialization values show up in Initialization field, and after switching to text view, we can see them here in our declaration. Now we can use this function block in the logic to configure our driver. First, we start typing a name, and system helps us with smart coding function. Then when we open brackets to configure inputs and outputs, system also automatically gives us a list. So in this case, to input driver config, we assign variable st CAN bus config, and no variable is assigned to output error. In the next step, we'll prepare a mask for message receiver. And first we'll prepare a handle. So we name it HMask receiver, and we assign to it a handle from our library. And then to configure this mask, we create a variable mask config type receiver mask taken from library. This is a structure and require initialization, so we switch to tabular mode and use initialization table. Here we keep all values default except X transmit mask, which we set to true. Now we'll make a logic for this mask configuration. It is not recommended to run this configuration continuously, so we run it only when our HMask receiver is invalid. And then we write to HMask receiver a value received from function block driver can 29-bit, method getMaskReceiver, and mask from configuration file mask.config. Next part of our logic is cyclic read of messages. So let's look into library, and this time we use method receiveMessage. This method has three inputs. First is receiver handle, and we already have it, our variable HMaskReceiver. Second is message processor, we prepared earlier. And third is time limit type time. Back in our program, first we create new local function block stMessageReceive, type message processor _st, and new variable tTime to receive, type time. This variable requires initialization, so we add here t.0 millisecond, and that means no time limit. Now call our function block driver can 29-bit, method receiveMessage with input HReceiver equal HMaskReceiver, input ITF message processor equal stMessageReceiver, and input tTime limit equal tTime to receive. And again, there is no variable assigned to output E error. Now our program is ready, but before we can run it, we must add it to PLC task. So we click on PLC task in task configuration, then add call, and then we select our program from list. Next, we compile our project, and if there are no errors, we can download and then test it. Now, after download and starting our program, let's look into our user variable global list, and right away we can see our variable receiveCanID changing value. That means we are receiving cyclic messages and reading their identifiers. We can show value of our variable in hexadecimal mode, slow down our recordings, and compare our values with examples of broadcasted messages from BMS system. So when we see, for example, value hex 18 FEEB 46, and knowing standard structure of message identifier frame, we can recognize that this message is coming from device address 70, hex 46, with parameter group number PGN equals hex FEEB, and priority, together with reserve bit and data page bit, equal hex 18. So we know that this message contains product ID. Next, we'll read the data field from our frame. We'll do it first for our message product ID with ident FEEB. And as a result, we should read a string of 8 bytes. So first we go offline and open our user variable global list. Here we add new global variable, myData FEEB, and it is an array from 0 to 7 of byte. Next, we'll open our method ProcessMessage, and here we first check if our identifier equals one for product ID. If yes, then we make a small loop with new variable I for our increments, and in this loop we insert into elements of our global array myData FEEB, matching elements of data field from our incoming message. After compiling, download and starting, we can see our program running, and when we look into our global variable, we can see our array with all data recorded and matching data from BMS example. According to BMS protocol, this product ID should be presented as string. So now we'll add the logic to convert our array of bytes into string. First we go offline and open our user variable global list, and then add new variable can product ID type string. The easiest way to convert this data is by assigning to both of them the same PLC address. So first we'll switch our view into tabular mode, and then assign address %MB3000 to both of them. After compile and download, we can see product ID as a string li3 *8 ****. Additionally, we can see that messages can be sent in different time intervals. So add the logic to count received messages. First, we'll create new global variable g_count message _FEEB type unsigned integer, and then we modify our logic in method ProcessMessage to count incoming messages. After compile and download, we can see our counter changing value every 5 seconds. Next, we'll work on the message 1FFFD that provides us battery voltage and current data. So first, like with product ID, we'll create two global variables dedicated to our message identifier 1FFFD. One variable is g_count_message 1FFFD type uint. Second variable is myData FFFD, and it is an array of bytes located in PLC memory location %MB 3008. Next, we move to our method ProcessMessage. And here, same like we did with product ID message, if our receive CAN ID equals hex 19FFFD46, then we increase our incoming message counter, and then in the loop, we insert into elements of our global array MyData1 FEED, matching elements of data field from our incoming message. Let's go back to message definitions of BMS system. Please note that product ID message has only one part, product ID text string. But DC source status 1 has 4 elements: instance, device priority, battery voltage, and battery current. So back in our global variable list, and here we add 4 new global variables. First is CAN instance 1FFFD, type unsigned integer. Second is CAN priority 1FFFD, also type unsigned integer. Third is CAN battery voltage, type real. And fourth is CAN battery current, type long real. Please note that all those results require conversion and sometimes additional calculations. So we'll create new program for that and name it PRCAN conversions. Inside this program, in first line, we convert instance. So our global variable CAN instance 1FFFD equals, and here we convert from byte to unsigned integer element 0 from array MyData 1FFFD. In second line, we did the same for priority. In third line, we need to make some calculations. So our global variable CAN battery voltage equals, and here we create new local supporting variable MyData1 FFFD voltage, type word, and those are bytes 2 and 3 of our message. Next, we convert it from word to real, and then multiply by precision factor 0.05. System right away asks us to declare this new variable. It is type word and address %MB 3010. Why address 3010? Our entire array for this message starts at address %MB 3008, so byte 2 would be at address 3010. Next, we'll add the conversion for last element of this message, battery current. So our global variable CAN battery current equals new variable MyData 1FFFD current, type double word converted to long real, minus offset converted from hexadecimal, and then multiplied by precision factor 0.001. And again, system asks us to declare our new variable. So it will be type double word and address %MB 3012. Our program is ready, so we add it to PLC task and then compile and download. After download and start, we can look into our global variable list and see active value for device instance equals default 1, priority equal default 120, battery voltage equal 209.7, and battery current equals 0. So our message receive program worked properly, and next we'll create a logic to send messages. First, let's see what commands are available with BMS system. And there are two of them. One, power on off with charge on command, and second, a request for proprietary data. So we'll use first one, and with it we will switch power on and off. But first we need a way to verify if our message was sent and successfully received by BMS system. So add additional diagnostic message to our receiving messages and monitor operating status. So back in global variable list, first we'll add a counter variable G count message 1 FECA and array my data 1 FECA. Then we add first operating status variable can should be always on type boolean, and then second operating status variable can power is on, also type boolean. Next we'll move to method ProcessMessage, and here we add standard loop to record data to our array myData1FECA. Program PR can conversions will assign message data elements to our global indicators. So our variable can should be always on will be controlled by myData1FECA element 0 bit 0, and variable can power is on will be controlled by myData1FECA element 0 and bit 2. Next we compile and download, then look into global variables, and here we can see that signal can should be always on is true, so our BMS is on. Signal can power is on is false, but we can activate it using BMS push button power on reset. Next we'll try a different way to power on and off our BMS. We'll send a GetBusMessage DC source command and monitor signal can power is on. First, let's look into library can API. This time we'll use a method sendMessage, and this method also requires input information and data in form of structure type message or extended structure type RX message. So next we'll go to our program PR can send receive and add new variable st message send type RX message. Next, we'll set initial values to this variable, but this time we'll do it in our program. So first element is st message send can identifier, and we put into it value hex 19 FEA4 46. Next, we'll configure our message identifier to be 29-bit. Next, we set the data length of our message to 8. and then we'll set values to data array we want to send. So into byte 0 of data array, we'll put value 1, since this is a default battery ID. For byte 1, we'll create new variable, desired power, type byte. And when this variable is set to 0, our command should turn battery power switch off, and with variable set to 1, our command should turn it on. With autodeclare, we make this variable global in our user variable global list, and then we move it to the top of this list. Back in our program PRCAN send receive, all remaining elements of data array will be set to 0. Next, we can implement method sendMessage in our program. But with the logic written like this, we are now simultaneously receiving and sending messages. So to avoid this, we will make a condition using new Boolean variable bSend. This variable will be also global, and we'll put it on the top of our user global variable list. So when this bit bSend is true, then we send messages, and if it is false, then we receive messages. In our test, we want to monitor BMS status signals all the time, so allow a message to be sent only one time after activation of the bit bSend, and then we reset this bit back to false. So let's test it. After compile and download, we'll look into active global variable list, and you can see that BMS system is still powered on. We can verify it on BMS unit and see that power indicator is continuously on. Our desired power bit is set to 0, and that means our command should power off the system. So first we prepare value true for our variable bSend, and then we push Ctrl F7 to write this new value. Right away we can see signal CAN power is on from BMS showing false, and BMS power indicator starts blinking. That means our command was sent and received properly, and battery power switch is off. We can also see that bit bSend was right away set back to false. Let's try again. This time we prepare value for desired power to 1 and bSend again to true. And after writing, we can see that CAN power is on shows true and command works properly. The last part of our example will be diagnostics. So again, let's look into library, and this time we'll use method GetBusDiagnosis. We can also see here that this method requires an in-out variable type diagnosis info. So we go back to our program PRCAN send receive, and add here new variable stCANdiag type diagnosis info. Next, in program body, we'll call our method GetBusDiagnosis and use our variable stCANdiag for in-out diagnostic info. And now we are ready to test it. After compile and download, we can see our program running, and after we click on our stCANdiag variable, we can see entire diagnostic structure. That was the last part of my presentation. Thank you for your attention.